Okay, so this is lecture 9, and let's go to the last slide of our lecture 8. Lecture 8 was interrupted due to a computer problem, but fortunately we have covered all of the contents we have planned at that time, so it's just okay to stop there. And now continue our discussion on how can we proceed to fabricate the FinFET in our virtual environment. And at the end of our previous lecture, so this was the last one we had. So okay, now here we have the final structure of our previous lecture. Let me just name them once again. This is corresponding to our silicon substrate. Yes, we have a very deep substrate, but only its surface part is shown. And here we have a green layer, which is corresponding to the pad oxide. So this is relatively thin compared with the other part. And this is to protect our silicon substrate. And here we have another one that is corresponding to the hard mask. Hard mask is usually made of silicon nitride. So the reason why hard means that actually silicon nitride is regarded as a rigid material in our constellation. So we say that this is a hard mask. And the final, when we have a look at the final structure of our previous lecture, we can find that we just transfer our initial structure in silicon dioxide into this silicon nitride hard mask. That was done. And another consideration is previously we had also here and there we had patterns. However, they are not used in our actual device fabrication, so we have just eliminated them. This part is called as a so-called fin cut. Fins are eliminated from our structure. So if we have this top view, so this fin cut is corresponding to having only fins corresponding to these three lines, and these unwanted fins shown as this gray shaded one, they are all eliminated by etching process. This is corresponding to fin ones and fin cuts. And here we have for example, here we have an inverter, and let's say that we have another inverter. If their fins are physically connected, if not eliminated by this fin cut process, then they can communicate the information. So that's the reason why we must introduce this fin cut structure. Okay, so now let's go to our main lecture, lecture 9. Today we will finish the fin formation. After that we will move to the next part, like dummy gate formation. Okay, and if you have any questions, then please interrupt me anytime. So okay, now let's go to our lecture. This one, yes, this one shows just TEM image of the real FinFET, actually the Intel one. So we can have a similar TEM images from different companies, but I just took the Intel's one. And here we have two different fins. Yes, we are currently using 3 fin structure, but 2 fin and 3 fin, that at the initial point that was the standard. And you know, now we are at the end of a FinFET era, and single fin is a relatively new technology. So previously we had multiple fins to reduce variation of this fin structure. So yes, so anyway, I already stressed that one already. So now I guess that this is oh sorry, I made 12 nanometer, so I have to check this exact number. But anyway, here we have fin, and what is the silicon, and this is corresponding to the silicon. So if I just the boundary between silicon and other material, then I have to draw in this way. Yes, this will be the shape of a fin. The reason why I'm showing this TM image is actually edge depths are different. So please have a look at this one and this one. Here we have a different profile. I mean that if we have two fins surrounding this gap, then actually this gap is relatively narrow. However, for example, let me just draw once again. If we have this kind of another island of fins, and in between we have nothing, so we have a much wider window for our etching process. So the reason why we have different etch depths is we must insert our etchant into this narrow hole and have a certain chemical reaction, and also the resultant material should escape from this deep and narrow hole. That is very difficult for this narrow one. But if we have a sufficiently wide structure, then it is easy to move into that part and also escape from that part. So that's the reason why if we have a wider window, usually etch depth is deeper, and if we have a narrow opening, then it is difficult to have sufficiently deep etch profile. So think about this one. How can we realize this kind of effect in our simulation? In order to consider this kind of simulation, then we have to consider actually surface reaction itself. So just to control the movement of etchant into that surface point, and if we have sufficient density of etchant, then reaction can occur quite rapidly. And if we have not enough high density, then the etch rate will be reduced. That effect should be considered to have this different etch depths. But unfortunately, right now we are just taking the change of shape itself. So when you have a look at this one, the resultant behavior, now you know that here we have place between these two fins, and here we have much separated by two active regions, and you know the etch depth is the same because we have not considered that effect in our calculation. But please be careful. In reality, we have to consider the chemical reaction. So it is not a magic to etch something, so to be etched, so that doesn't work. Actually, we just provide something and provide some good environment for chemical reaction. So that is a non-ideal effect we cannot consider right now. So please understand, although we treat it as just a flat surface over here, but you have to understand we can have a little bit deeper and a little bit shallower profile for our fin definition. Okay, and this is the one we are using to make this kind of etching process. Well, anyway, Maybe you remember the numbers. So target fin height is 32 nanometer, and also STI depth is very much comparable to that of fin height. So if we just schematically draw this fin structure, then we can just draw one fin structure, and half of it is filled with so-called STI, shallow trench isolation, and half of it is just open to the external environment. And of course, when we ask what is the effective fin thickness, then we have to say that this is corresponding to the effective fin thickness. Of course, here we have a hidden structure to support our fin. However, electrical sense, that doesn't make any contribution to our current conduction, because we just collect our electrons and holes by action of here gate contact, and only the region where covered by gate contact will collect a certain amount of electron gas or hole gas. So this part is not active in collecting charge carriers. So that is the number we have. And this 32 is actually corresponding to the old time technology, not for 7 nanometer, and you know that it is much taller, like 50 or even taller. But for a while, I will just follow the ASAP 7 PDK, so please understand this one. Maybe later, when you do your own exercise, maybe you can play with different fin sizes. So for example, I wanted to make an even taller fin, and I wanted to make an even narrower fin. That can be your possibility to even further optimize this system. Obviously, the best thing is narrow fin and tall fin. So if I am allowed to whatever I can do, then I would like to say this extremely thin and extremely tall fin. And then since this fin height is too high, very high, I can collect a lot of charge in it, and also my current will be quite high. Very good. But unfortunately, if we try to make this structure very narrow and tall, then actually it has some mechanical problem. So this now it is no longer a rigid body, but it's like just a paper, a sheet of paper, and there another neighboring same structure, and their distance is currently just about 20 nanometer. And if we have a even further scaled one, then they can be even closer. So in that case, they can be leaned into same direction, for example, or they can be merged into each other. So this kind of a mechanical problem can occur. So that's the reason why we cannot increase our fin height indefinitely. Well, I wanted to increase as much as possible, because this is a very good way to increase effective thickness without sacrificing the silicon area. If we make a very tall one, but when you have a look at just top of it, yes, please try to look this structure, then you will just see area consumption corresponding to this one. If you have even taller structure like this one, even when you have this extremely tall fin, but if we consider area consumed by our same device is the same, but effectively we have a lot more current. So that is just like a magic or certain trick, but the price is quite clear. You cannot make it. So if you try to make it, then there will be some problems. So if your engineers can manage it, that kind of a mechanical problem, then that's good, and your company will win this competition. But we have to obey the natural law by physics and chemistry and something. So it is very difficult to beat this one. So we have to not not to exaggerate its fin height. But anyway, in terms of history, so 7 nanometer technology already achieved much taller fin height, but we will use this one. Well, so now you understand this profile is not perfect. It's a little bit idealized. The depths, edge depths can be different, but anyway, please try to do that. How can you do that? Where can you find the actual statement for etching? So please do your own exercise, I guess. So now you can do it by yourself. And now the next part is fill the STI. So as I told you before, STI should be filled about halfway of our entire fin, tall fin height. Okay, so then maybe you can think about in this way. Well, since we have to fill 30 nanometer thick STI, just to do 30 nanometer thick STI fill. Then if we just try 30 nanometer STI fill, then what will happen? Please guess. Then in this case, maybe we can have half of this part is filled with STI, and also it is filled with STI, Seems like good, and it fits to our purpose, but it's not. So if you do it in that way, there is no control about the precise control on this part, because depending on this pattern, your starting point itself is different. And how can you also control this sidewall growth? So if you just put your STI in isotropic way, then your shape will be just like that will be your final structure after 30 nanometer oxide deposition. So you wanted to selectively fill only the space between fins. That is a STI, but you fail to do that. So that's the reason why from now on we'll talk about how can we do this job with a more reasonable sense. That is, in some sense, quite easy in theory, but not that easy in practice. Here, as you can see, we are just depositing quite thick STI. STI is silicon dioxide. So this is not final structure after this deposition. Of course, since the original structure, our structure have some grooves here due to the existence of fin structure. Of course, it will show higher, taller structure, and it will show relatively shorter structure. So there will be certain amount of still remaining level difference here. And now this is the trick. Here we perform CMP, chemical mechanical policing. So chemical mechanical policing means that using both method, chemical and mechanical way together, make the planarization of a certain structure. Simply speaking, we just introduce something called as a slurry, and slurry is some like a sand, yeah, in some sense. And if that has a certain very fine grain in it, and we just introduce certain rotating structure, and it is slowly, very slowly grinding our structure from the top. Let's just say that originally we have a certain uh, differences in here, and say that this is the surface of our CMP machine. So it is now rotating in that way, and just to go down. So since there is nothing left, so it's okay. But when it hits our surface, then suddenly its movement will be quite slow because it should remove the surface material. Okay, so after a little bit later, then we can advance a little bit and little bit. So depending on the composition of our surface, actually the speed of our CMP advancement is really dependent. If there is an easy material, then it can advance quite fast. And if there is a difficult material, not that effective in this CMP process, then advancement will be quite slow. And at the same time, in this CMP machine, we have always have a certain monitoring system to take into account the change of the surface. So whenever the CMP rate is rapidly changing, then we can immediately understand there happens something, some changes in the material composition. So think about this one. Here we have let me just draw this cross-sectional view of our structure. So please understand my drawing is not perfect, but anyway, let's say that this is a silicon surface, and now we have certain, this is corresponding to hard mask, and also we have introduced very thick, yes, this is corresponding to our silicon dioxide in this case, SiO2, and here we have silicon nitride, and try perform this CMP. When we have this structure, then obviously when the level of our CMP is around this structure, then this polishing is mainly determined by the rate of silicon dioxide. So it is almost constant. And let's think about the level around here. So if its front is shown here, then still we will have that of silicon dioxide. And if we touch this top surface, then what will happen? Of course, some part is easier. However, some part it is not that easier. But you know, this structure, this machine is not flexible structure. It is really a rigid body. So if there is a certain rigid material, then although this part is easier to be polished, but we cannot proceed. The worst one just determines the actual front movement. Then our monitoring system really recognizes that, oh, there is something resisting against our front movement. Then we say that, oh, that is corresponding to this silicon nitride. Material changes can be quite sensitively detected by this CMP process. So that's the reason why now once we have this one, then that is used as a stopping signal. Oh, please stop. Now we have already touched this hard mask layer. then maybe you can ask me this question. It means that everything is perfect, but due to certain variation, for example, instead of this perfectly uniform uh, height, what happens if we have a slightly shorter mask here, and if we stop here, then maybe this silicon nitride is not fully exposed to our surface. In that case, in order to reduce such kind of a risk, so what we do is first stop the CMP, although not shown here due to the ideal structure we are currently considering. In reality, we insert additional over etching. Slightly the upper part is etched away, so then if our structure is within certain amount of variation and this top part is clearly cut, and we will have this structure perfectly. So that is the way we do CMP. So I remember that actually when I study in my own PhD course, CMP was relatively regarded as how can I say, large scale process for less advanced one, because at the time their control was not that exact or not that accurate. However, nowadays, if we have a look at the process integration in our state-of-the-art devices, actually use of CMP is widespread. In many cases, we always try to perform this CMP to make a planarization, because once we make this planarization, then we have the same starting point, and it is easy to control the final profile. Otherwise, maybe if our starting profile has some differences depending on the position, then the uniformity of our final result can be also quite high. So that's the reason why we are using CMP extensively. And natural question is, then is CMP is free? No, CMP is not free. So therefore, we have to also perform a lot of effort to develop and use this CMP. But anyway, this is the way we fit this plane surface. Now it is certain that, okay, why it is important to reveal this hard mask? Now we have clear hard mask shown here and oxide there. Then by using certain etchant have quite a good selectivity between hard mask, nitride and silicon dioxide. Now we can keep this one, then remove other STI, overgrown STI quite clearly, and so now you can see that this is the result of our etching process. Of course, where is hard mask? After this is over, then of course STI or okay, so sorry, also hard mask should be removed, but this is the result of our structure. So please have a look at this structure. Now later this part will be N MOSFETs, and this part will be P MOSFETs, and in between here we have intentionally erased our fins. The reason why we have this one, of course, isolation, and we will have also shared gate contact between them. Means that here we have a P MOSFET and here we have a M MOSFET. Both of them should be driven by the same gate signal. You know, in order to make inverter, we have to provide the same gate voltage to both MOSFET gates and PMOSFET gates. So they are connected by a single metal gate connecting these two parts. So this part is used for that purpose. And you can see that there is another space is here, and this part is to just separate our cell from the other. And another one is, in order to, up to now, I just to show you that this is corresponding to the gate metal. Gate metal is corresponding to the input signal. Then where can you find the output? Then how can you put this output? So that will be discussed later. And another one is another signal, input signal, output signal. They are time varying voltage, and also we have to support ground, and also we have to support VDD. They should be supplied to this structure. And where can we just accommodate those power lines? And those power lines will be accommodated in this part and that part. Which one is which one? Since this is regarded as a MOSFET, so we need ground here. And since this part is regarded as a PMOSFET, so we must provide VDD nearby PMOSFET. So this will be discussed later, but please just certain imagination what will happen to this structure. So now, yes, so we can do this kind of thing just to eliminate the silicon dioxide and silicon nitride. This is hard mask. Hard mask is gone. Yes. After that, we will have this is thickness 3 of silicon dioxide. What is it? This is pad oxide just beneath of hard mask that is eliminated in this case. But please note that my final question on this slide is like this. This final structure shown here is highly idealized. Highly idealized means that first of all, we have assumed that this plane bottom of STI layer is flat. However, depending on pattern, we can have a different initial point for this STI part. That is one thing. And another one is here you can see that the shape just looks like this. It's not that much straight, or not upright, but it is narrowing down when you go to deeper and deeper. Why do we have such kind of a narrowing effect in this etching profile? So first of all, if this is deep enough, then it becomes increasingly difficult to insert our chemical component into that deep. So that's the reason why our etch rate becomes slower and slower, and that is one reason. But in some sense, it is not that much bad effect, because we always wanted to have a very flat structure in this thin part, because it is really required. We need, so I will explain it later. But anyway, this upright pattern or surface is quite important for optimizing the structure. But what is the role of this relatively lower part? This part is just working as supporting, mechanically supporting layer for our electrically active fin layer. So therefore, actually we don't have to this perfectly upright structure. It is completely okay to have a relatively fat and upright structure. We will use only this part for our electrical conduction, and this part is used just a supporting layer. So that is not that bad to have this kind of structure. So right now, our shape just to looks like this, but it is clear that if we can have the structure like this, yes, if we can have such a structure, it would be much better for stability of our fins. So there are two consideration about it. So let me just finish this one. The final structure we are currently considering in fin structure is highly idealized. The shape is not that easy as drawn in our constellation. So please understand the limitation of our simulation or emulation. And another one, the the real last one is here. I have introduced H without specification, and the default behavior of our code is when you just call H without further specification, it is regarded as Z directional anisotropic etching process. However, in reality, instead of this anisotropic etching, it is known that this this procedure called as a fin reveal is regarded as an isotropic etching process. So I tried to have a good enough profile with isotropic etching, but eventually I failed. So that's the reason why I just made this simplified one. So, but please note that in this case we are using in reality isotropic etching. So now anyway, this is the current situation. Please have a look at these two graphs, one from ASAP PDK, the right one, and left one is the one we have done up to now. So when you make a comparison, now you can understand we made this fin patterning and STI is fielded. However, we have more structure to be implemented, so that is also contents in our today's lecture. Okay, so that is the one we will consider. But looks quite well matched to this one, because ASAP 7 PDK reveals all over the detailed information. So for me, it was not that difficult to follow the exact numbers. So okay, let me make some midterm summary on our process emulation. We have just done the very first part found in our literature. When we have research papers, so simply they show process fabrication process, and this fin patterning is on top of that list. First make a fin. Yes, it is like just granted, but you have seen that in order to make this simple structure with uniformly placed fins and patterned with active lesions, we have to do so many times etching, deposition, etching, patterning, blah, blah, blah. So it is very easy to say something. However, in reality, we have to introduce several intermediate steps, and every steps in our process can introduce errors, especially mismatch. So since that everything is just in scale of nanometer scale, if one step and next step has a certain mismatch by amount of 1 nanometer, then so that can be critical for our final device performance. So that is a difficult thing. In reality, we are just make a sketch on fabrication process. So please understand the limitation of our discussion. So our structure is far from the realistic one, so we have a limited capability. But in my opinion, even though, but it is much better than doing nothing. So I think that this is not easy to get from usual textbook. So let's keep this kind of study further to finish our FinFET fabrication process. Okay, so now the next part of course is to make gate. But I have to say this one. Oh, now we have fins and the position where fins and gates are meet together. This part is regarded as MOSFET channel. So now let's make the gate. That can be a usual way to think, but unfortunately, so this fin we have made. These are fins, and they are real fins. We will use these fins as a channel material later on. But here, from now on, we will try to make this gate structure to define the channel. However, one important point is our gate from now on is not the real gate. That is the point. So they are called as dummy gates. Dummy gates, and the role of these dummy gates is quite simple. They are used as just a placeholder. So this part will be the channel. So please do not touch this part. This part will be covered by dummy gates. That is the role of dummy gates. Then maybe you can ask me this question: why we have to introduce this kind of complicated procedure? Why don't you just start the real gates directly? But unfortunately, it's not that easy to do it, because although we are not talking about that much, there is always concern about heat, the fabrication temperature. So gate first is not suitable for our full integration. So the standard way is first introduce dummy gate, which will be eventually eliminated. So this is important. Dummy gates, and together with this dummy gate we will have dummy dielectric. They are pairs, and these dummy gates will be removed later on. And only reason why we introduce this dummy gate is to define dummy gate. Think about this one. Now we have a CPP. What is the assumed CPP of our process? Do you remember? This is 54 nanometer. And now this 54 nanometer should be divided into some parts. One is, of course, the majority should be given to our gate length. Gate length is required. And for other parts, here and there, we have to accommodate our source and drain. Wow. Then let's say that gate is equal to 20 nanometer. Then what does it mean? If we have a 54 nanometer as a CPP, and if we have a gate length of 20 nanometer, and we have only 34 nanometer for two source drain regions. Okay, let's make it even. 17 and 17 nanometer. Okay, so 17 nanometer is assigned to source and 17 nanometer assigned to drain. So let's assume that way. We did it. Then what happened? here we have sorry, okay, let me just show this one. Here we have a gate, and here we have a source, and here we have a drain. Then question is, where do we have isolation between these three different contacts? So gate is metal gate, and source drain, yes, source and drain is highly doped N plus or P plus resin connected to another metal. So basically three of them are all metals, and if they are attached together, then there is no isolation. So simply speaking, in this structure, even this short 17 nanometer should be divided, and our source have just a portion of this 17 nanometer, and in between them we have to introduce a certain intermediate layer to separate source and gate, and also separate source, drain and gate. These are required, so it is quite tight. Okay. So now we will think about this one. Okay. So CPP is 54, and now we have this kind of relatively tight length scale, so we have to be very careful about doing something. And well, anyway, the dummy dielectric, so its typical value is around 2 nanometer or well, about 3 nanometer, depending on case, as much as I understand. And please understand, the native oxide thickness of silicon on top of silicon is just 0.7 nanometer. So even without doing anything, so if you just expose it to your silicon onto the air, then the one layer of silicon dioxide native layer is formed, and it is about 0.7 nanometer. So we intentionally cross a little bit thicker one, and this is used to protect our fins. So this one is drawn. After that, let me just explain once again. Where can you find your MOSFET, and where can you find your PMOSFET? Of course, it is symmetric, the structure right now, but let's say that this is for your MOSFET, and now this is your PMOSFET, and if we draw in top view, we will have 3 lines and 3 lines for MOSFET and PMOSFET. So these 3 lines is corresponding to these 3 lines, and these 3 lines is corresponding to these 3 lines. So the horizontal direction is the direction where fins are running. Fins are running in this horizontal direction. Then in order to make a cross point between fins and gates, what should be the direction for our gate running? Gate should run obviously in, oh sorry, I have to draw straight line. I will try. We have to have the vertical line in our layout design. That should be the direction for our gate. And in this 3-dimensional structure, please try to draw your own gate. Your gate should run in this way. And you have to also have a different one, and the minimum size, more minimum spacing or minimum pitch between these two lines is called as a CPP, and this is 54 nanometer in this case. Okay, so simply speaking, although we are saying that this is corresponding to 7 nanometer technology, but 7 nanometer is not for your gate length. Your gate length is much longer, 20, and the CPP is not a multiple of your number 7. So 54 divided by 7, it doesn't give us an integer number. So, well, there is no 7 in this case. Maybe you can make some can I say, relation between fin thickness and node number. Somebody says in that way, 7 nanometer has the fin thickness of 7 nanometer, and if we go to 5 nanometer technology, then fin width, fin thickness becomes narrower, so close to 5 nanometer. But it doesn't mean that TSMC's 3 nanometer technology have 3 nanometer fin. It's not. So fin thickness is more or less controlled around 5 nanometer. 5 nanometer is almost the extreme value we have. So that relation is not that strong. So please regard just this number, node number, as just a brand name or code name for our development, our field. So now we have to draw dummy gate. Dummy gate should be placed with a pitch of 54 nanometer. Then can you find any lithography which can realize 54 nanometer pitch except for EUV? So the answer is no, it's not possible to realize 54 EUV. Oh, then you can ask me this question. Well, previously we have assumed that existence of 54 pitch lines, and from that one, by applying self-aligned double patterning, SADP, we were able to fin pitch of 27 nanometer. We did it, but that was our assumption. There is actually no lithography which can make a 54 nanometer pitch lines. So in this case, we have to also start from for example, assumption of 108 nanometer and perform SADP and down to 54 nanometer fin size. That should be done. Okay, so before talking about patterning, first of all, we have to deposit this dummy gates. The target thickness of dummy gate is set to be 95 nanometer. And where do we have this number? So, well, I have taken this number from iMac paper, but I'm not that sure this number is definitely right. Of course, known range is around 80 to 100. So this is known thickness of dummy gate, but what is it? Is it exact? I have a little idea. And another one is I'm assuming that we are doing CMP after this dummy gate deposition. So please have a look at this iMac figure. So at the beginning, we have this fin structure. Yes, now we have a fin structure, and that is filled with this STI. This one is STI. Good. Up to now, we have done. And previously, we just introduced dummy dielectric. Yes, this green one. So can you see it clearly? So let me just enlarge it as much as possible. So that this is, oh, good. about that. So please. Oh, why don't you just kill it? Let me just start it again and go to, oh yes, so now let me just more slowly. Oh, can you see? Okay, in this scale maybe I'm not that wrong. Then in this okay, so I'm not I can see a green line, but I have a very low vision, so maybe there is no drawing. Sorry about that. But anyway, here we have now we now have this one. This is corresponding to our dummy dielectric. We just introduce it. After that, what we do is here now dummy gate deposition. Since we have once again level difference from our initial starting point, so if we just make isotropic deposition of dummy gate material, then obviously we will have this kind of level difference in our final structure. In this paper, the IMEC researchers suggest that they have developed the CMP process to planize this dummy gate deposition. So you can see that this is the one, and yes, this is the one they suggest, but it is not that clear. This CMP process is really used in mass production or not, so but this is just I'm following this kind of CMP process to make it easy. So at the beginning I lived without this planarization, then the final pattern looks quite in some sense ugly and up and down, and by adopting this CMP, shape becomes quite beautiful and straightforward. That's the reason why I'm taking this option, but I'm not sure this is really mandatory or not. So anyway, we have this final structure. This structure is corresponding to the deposited dummy gate. In this graph, blue one is corresponding to dummy gate, and dummy gates are usually made of amorphous silicon or polysilicon. So right now I'm assuming amorphous silicon, but there are also polysilicon. I think that polysilicon is more frequently, seems to be frequently used in this case. But anyway, if we provide a certain heat, then this amorphous silicon just turns into polycrystalline silicon. So the final result is the same. But anyway, now we have a planarized dummy gate, but there is no patterning error. We must pattern it. The lower part is just showing what is behind this dummy gate. Now we have well-defined fins here, and what we want to do is just to draw these lines to perpendicular to this fin direction. So okay. So how can I say, I made mistakes in my explanation. I just I think that I made mistakes in my drawing. Here we have this part is corresponding to the dummy gate, and now we wanted to make a pattern on this dummy gate. Yes, let's do it, but this is not the way we do. Whenever we do such kind of lithography, then the only thing that can be patterned is photoresistor. We cannot make the pattern on our amorphous silicon. No, it's not possible. So therefore, we have to introduce a photoresistor. But now you understand. Yes, amorphous silicon. Although we wanted to pattern it, so since it is not possible, so we introduce PR. That's enough. But point is, almost always in this case, we have to introduce another intermediate step called as hard mask, because photoresistor is usually organic material which is not strong enough, so we have to have silicon nitride to keep this structure. Maybe you remember this one. Previously, when we considered this SADP or SAQP, we introduced silicon dioxide sidewall as a final pattern. But even that case, we considered silicon dioxide sidewall is not strong enough to be used our patterning. Eventually, we had to introduce hard mask layer. So once set or transfer our initial pattern into hard mask, and from hard mask to the later pattern should be made. Quite similarly, even in this case, we have to introduce hard mask. So things becomes quite complicated. Dummy gate, and here we have a hard mask corresponding to silicon nitride, and of course we have to have finally PR, photoresist, and this photoresist is patterned, and using this photoresist as a mask, now hard mask will be patterned. Long story. So let me just show you this table. This is the lithography rules assumed in ASAP7 PDK, and as you can see here, even our gate is patterned with SADP, double patterning, and its pitch is 54. So we have to have this kind of quite complicated one. So I will not show you the detail, but please just guess what are needed. If we have to perform another SADP, it means that we have to also introduce mandrel layer, photoresist layer, and photoresist patterning, and mandrel etching, and sidewall deposition, and anisotropic etching, mandrel removal, hard mask etching. So that those kind of things are required. If you cannot imagine the procedure I'm talking right now, then please review our previous lectures. You should, as an engineer related in this VLSI sim, you should be able to imagine what will happen in this structure. That is very much difficult, but anyway, we have to do it. So I will skip them all. So just to assume that by performing all kinds of these efforts, now our hard mask is patterned, and let's go to that patterned hard mask. Well, now you are looking at this hard mask, and this hard mask is patterned. The pitch is, as we assumed, the pitch is 54 nanometer, and the length of a gate, dummy gate, is given as 20 nanometer. 20 nanometer is for 7 nanometer node, okay? Then one question we may have is, okay, we understand length is quite long, like 20 nanometer. And even with the state-of-the-art devices like 3 nanometer or 2 nanometer, it is not that much scaled down. So its value is around now 16, 14, around something. These are current value we are using in the state-of-the-art device. Then natural question is, then what will be the ultimate value of gate length in silicon technology? That is a quite important question, because our CPP, now you understand, our CPP is made of these components. CPP is a sum of gate length and also 2 times of spacer length and 2 times of half source drain length. So if you don't understand right now, so I will explain it later. But anyway, it is certain that CPP contains many different components, and change in our gate length directly reduce the CPP. And area of our logic cell is given by just CPP times, this is cell height. So if we can reduce this CPP directly, then it represents real reduction of our standard cell. So therefore, reducing this gate length is quite important. So we had 1 week online, 1 week long online lecture due to my business trip, and I have been in Munich, Germany, to attend the ESSERC conference, and there was a presentation by Huawei, and they say that maybe with this silicon technology, the minimum gate length we can achieve would be about 12 nanometer. We are 2 nanometer away from the extreme limit of silicon technology. So if we make it down to 12 nanometer, it is more or less manageable. But if we go to even shorter, even Huawei guys say that it's not possible, it's not realistic. So yes, anyway, the reason why I'm talking about this one, although we are talking about this 20 nanometer gate length, that is not that much exaggerated, and 20 at the time 20 nanometer was the real number, quite close, and the extreme number we will get in future would be 12 nanometer. And yes, now we have covered the contents here. 20 nanometer thick pattern, and gate pitch is CPP is 54 nanometer. Then now here we have hard mask pattern, but this is just hard mask, silicon nitride. In the next step, we have to etch this part away and also this part away. Then we will have the real dummy gate pattern on amorphous silicon layer. Okay, so I will not show that one. Please do your own exercise. So now you feel that whenever every step is added to your example, you have to wait for a few minutes. So please do not make any mistakes and typo in your exercise. Then you have to just to waste your another few minutes and again and again. So please be careful. And now you okay. So now, although I'm not showing the details, but you can do the dummy gate patterning. So now you can see that here. This is still hard mask, and this is dummy gate, and now you are looking at this green one is STI, and also our fin is covered and protected by a dummy dielectric we have introduced. So now check the status. This is the comparison between our inverter layout in ASAP7 PDK and our structure. Our fins previously shown is now hidden in this top view, but we all know that there are 3 fins here and also 3 fins there. We understand this one, and now we have make this dummy gate. When you make a comparison, especially for your dummy gate, you can find some differences between layout and our realization. What is the difference? So I gave you the hints. Here you have this dashed circles. Here you have a dashed circle layer, and in this case, now we have a dummy gate, and also dummy gate. And you can see that here you don't have a dummy gate, you don't have a dummy gate, there is no dummy gate at all. It is quite clear because this is P MOSFET and N MOSFET in a same inverter, so they should share the input signal. It is quite obvious. But another one is, if this line runs indefinitely up to the overcoming the cell boundary and another cell boundary, then it means that this signal is also affecting different inverter or different standard cell. So it is not acceptable. So we have to make this kind of cut, another cut. Let's name it as what? Now we have to cut the dummy gate. So we need gate cut. You can ask me this question: why we have to do this kind of tedious job? For example, in the case of a fin cut, we first draw long fin line, after that we erase it. Quite similarly, we are now trying to draw long gate line and try to eliminate it. Natural question is, instead of drawing erase, why don't you just draw some segment only for required fields, just to make it? And for example, for this part, do not draw it. But point is, how did you draw this 54 pitch line, or how did you draw this 27 pitch line? You have used not directly but SADP or SAQP. In the case, you have to make a sidewall. And when you talk about sidewall, if you just stop here, then what will happen? So sidewall will be made. So this, let's say that this is the pattern, this is the gate pattern, and if we stop here, this is corresponding to the mandrel, then we will have also the sidewall covering in this way. So it is almost impossible if we use this kind of a double patterning or quadruple patterning to make disconnected segments in its running direction. So unfortunately, we have to draw long line, extremely long line. After that, once make it uniformly, then just cut for unwanted one. That's the reason why this kind of a gate cut, fin cut those steps are required. Okay, so we will talk about this one later. And our homework is quite simple. You have a long time to finish this homework number 9. Just to follow our lecture material by your own exercise and attach the screenshots you have achieved. So most of information is already given in our lecture contents, lecture material, so you can just do it. Please be patient, and that it takes several minutes to once try that one. And another one is please please don't be too ambitious about achieving this final structure. Even myself are struggling to get these example structures currently I'm showing. I'm spending my almost 100 times fabricating these examples. So therefore you are not just following the lecture material, but you must expect that considerable amount of your hours should be spent to this kind of exercise to fully understand the structure. Okay, so let's meet once again 2 weeks later, October 13th, Monday, and please finish it or catch up our lecture blocks by then. Okay, I see that this is a really good chance for you to make up your slow down process. Okay, that's it. So do you have any question about today's lecture? No? Please. Yes. Yes. So if you, first of all, thank you for your question. And this deep substrate is intentionally set to be just 1 nanometer because it never etched or nothing happens in the deep substrate. And I intentionally set the thickness of this lead silicon thickness as 99 nanometer. So sum of these two ones, so silicon bulk and deep substrate, intentionally set to be just 100 nanometer. So you can say that this position is coordinate z equal to 100. Okay, so that is quite straightforward. So maybe you can ask me this question. So number 100 is enough or not? So in my opinion, if we take the fin height of 32 nanometer, it is just okay because we have enough margin. But if we consider more realistic one, the fin taller than 50 nanometer, then this 100 nanometer thick substrate is not sufficient. Of course, we have to have twice that fin height, and also we have to have this supporting layer, of course. So it is recommended to have a thicker structure. But right now, just to follow the exact coordinate, then that will be just 100. Okay. Good question. Any other question from our students? Okay, so if you have any question, then please send me an email because there is no written manual for this code right now. So unfortunately, I'm the sole guy to answer your question about this problem or bugs in this code. Okay. Okay, then let's wrap up today's lecture. Thank you.